Hey everybody. So we're going to do a little bit more in this video with vectors. So last time, let me just kind of summarize where we got to. We had vectors, these quantities that are have magnitude and direction, but we had figured out that we could write vectors in what we call component form, and we had the following. Let's say we had two vectors, v, which is v1, v2, v3, and u, which is u1, u2, u3. We defined a few things. Let's see. Oh, and we have a scalar. Let's say the scalar c. Right? Scalar just means a number. We have the magnitude of v. This is the size, the length of the arrow that we represent vectors with geometrically. And it's going to be the sum of the squares of the components of v, right? These are our three components, the x component, y component, z component. We said that when we add vectors, we will simply add their components, their corresponding components. And then scalar multiplication of vectors is defined by scaling each component, right? CV2, CV3. Okay, so there I believe is what we had looked at last time. So I want to go ahead and list a whole bunch of properties. So there's a whole bunch of properties that kind of come directly from these. I'm not going to go through proving all of them, but we'll look at a few of them in detail. So let's add, let's just say it this way. Our properties of vectors. So we're going to have, in this case, I'm going to need the vector u, v, and w, and then we'll have two scalars c and d. Okay? So some of these we've seen already. For instance, one of our properties is that vector addition commutes, right? We can switch the order. It's pretty simple to see when we talk about this in terms of the component addition, right? We showed it geometrically last time, but with components, very easy to see because we already know addition commutes here. So all you're doing is switching the order of these, but the numbers are going to remain the same. We also have that vector addition is associative. Right? We can decide to do different ones first or second, right? Or group them differently and everything will be fine. Again, you can check this pretty easily with components. We have a pretty obvious one. If you add the 0 vector, which is just the vector with component 0, 0, 0, you of course get the same vector fast back. If you add two vectors together and then scale it, that's the same as scaling each vector and then adding them together. And then let's see, if we add two scalars together and multiply them by a vector, that's going to be the same as multiplying each scalar times the vector and then adding those two resultants together, right? In other words, scalar multiplication distributes over vector addition, and then vice versa, that we have scalar addition distributes with scalar multiplication to vectors, right? So it distributes in both ways that are convenient to us. Again, some of this stuff seems like obvious, except we're going to see shortly some things that don't behave in, I would call these the nicest ways possible. What else do we have? If I take the product of two scalars and then multiply my vector by it, I could get the same result by scaling the vector by one of the scalars, then scaling again by the other. We'll end up with the same thing. And then, of course, if I scale a vector by 1, I just get the vector itself. Okay. So I don't want to go through all of them, but I'll just pick one of them to do. Let's show this one, distribution here, right? So let's just show it. Let's see. I'll show it abstractly and then do a quick example. So let's say I have u and v U and V as I've named them already. So U is equal to U1, V1, U1, U2, U3. V is equal to V1, V2, V3, and then I have a scalar C. What I want to show is that if I multiply C by U plus V, I get the same thing as multiplying C by U and adding it to C times V. Okay, so let's just do each side of this. Let's start by computing U plus V is equal to U1 plus V1 times U2 plus V2, and then U3 plus V3. And then if I take C times this, the rule is I just multiply each component by C. So I'm going to multiply each of these components by C. C times U1 plus V1, C times U2 plus V2, and C times U3 plus V3. Now remember, these are all numbers in here, right? The vector is this whole thing, but these are numbers in here. And these behave just like any numbers do, and we already know about distribution with regular old numbers. So let's just go ahead and distribute these two. I have CU1 plus CV1, that's my first component, CU2 plus CV2, and CU3 plus CV3, okay? That's what's going on the left-hand side, right? Now, let's compute this side. So let's take, we want to do, I'll just compute CU and CV separately. CU is just equal to CU1, CU2, CU3. CV is equal to CV1, CV2, CV3, which means CU plus CV is equal to, I just add components, CU1 plus CU2, sorry, CU1 plus CV1, CU2 plus CV2, CU3 plus CV3, right? I'm just adding each component. And lo and behold, that is precisely what we got down here, right? So it's just simple algebra shows us that these two things are absolutely true, right? By the definitions we've come up with, right? And I won't go through all of them, but all of them have the similar structure, that it's pretty simple algebra problems that rely on a lot of times the distributive property and commutative or associative properties of regular addition translates into vector addition because of the way that they're defined, okay? All right, let's add one more piece to this, a couple more pieces to this. So there are a couple special vectors that we like. We call these standard basis vectors. Okay, and there are three of them. Okay, and the three vectors are, so people name them differently. So we sometimes call them the vector I, the vector J, and the vector K. Sometimes they're written this way with these little triangular shapes above them, and people call them I hat, J hat, and K hat. I use both. I'll try to, it'll be pretty obvious what we're talking about. So I, J, and K, this is the vector 1, 0, 0. This is the vector 0, 1, 0. This is the vector 0, 0, 1. So first of all, geometrically, what these vectors are, if we think about our three-dimensional space, X, Y, Z, then I, or I hat, is the vector that moves one unit out on the x-axis. J is the one that moves one unit out on the y-axis, and then k is the one that moves 1 unit up the z-axis, right? Those are our three. I don't know why there it is. Okay, sorry about that. And those are our standard basis vectors, I, j, and k, right? Each one aligned to one of our coordinate axes. If you're in 2 dimensions, you can just take away k and you get I and j, right? You won't have third components, 1, 0, and 0, 1, okay? And those are the basis vectors. One thing we like about these, or one thing that we can notice about these, which often seems more complicated in the beginning but can be a useful fact later down the road, is that we can write any vector in our 3-dimensional vector system built out of these basis vectors, right? So for example, if I have the vector v equals 2, -1, 7, right? So I can think of this vector as, let's do a few things, 2, 0, 0, plus 0, -1, 0, plus 0, 0, 7, right? What would I do? I would add these up component by component. I get the same vector, right? Well, let's do one more move here. Right? So 2 times this vector, just multiply by the components, you get a 2, then 0, 0, you get this one. Multiply -1, you get this one. 7, you get this one, right? Well, notice what's sitting right here. This is just 2 I hat -1 j hat plus 7 k hat, right? So I can write the vector v as a combination of these. Sometimes we say as a linear combination of the basis vectors, right? And this is true for every single vector, right? More generally, if I have the vector u equals u1, u2, u3, I can write it as u1i plus u2j plus u3k hat. Right? So we can write any vector as a combination of these standard basis vectors, right? Again, this looks horribly complicated, right? Why would I want this over that? But it turns out to be an important fact about vectors whose usefulness takes a little while to see, but it is definitely a useful fact. And finding, well, I don't want to go too far down that road, but basis vectors are a super important part of the study of vectors and linear algebra when you get into those kinds of things. Okay, one more piece. I promise really just one more piece, and I'll give one example. These 3 vectors, notice, all have the magnitude of I is equal to the magnitude of j is equal to the magnitude of k. They all have a magnitude of 1, right? You take 1 squared plus 0 squared plus 0 squared and take the square root, you get 1. So they're all a single unit long, right? These are called unit vectors. Right? It's just vectors, unsurprisingly, whose length or magnitude is 1. Okay. We also like unit vectors for a variety of reasons, and finding unit vectors is going to be a useful tool for us. So let's take a vector and find its unit vector. If I have the vector v with components v1, v2, v3, I want to find a unit vector in the direction of v. Okay. Well, how do we get direct vectors in the same direction as another vector but a different length? By scaling them, right? So if I have the vector v, right? Let's pretend it's bigger than 1. What I would want to find is a vector whose length is just 1 in the same direction, right? So what might occur to us is, why don't we find out the length of v? Right? Well, if we know that this is the length of v, if we want to scale that to 1, we simply scale it by the reciprocal of the length, right? If v is 5 units long and we scale it by 1/5, we'll be doing great. If v is 1/3 of a unit long, we scale it by the reciprocal, we make it 3 times bigger, it's going to be a unit length. So it's always going to be the reciprocal. In other words, the unit vector in the direction of v is going to be, we're going to take v and scale it by the reciprocal of the magnitude of v. 1 over magnitude of v. Notice this is a number, right? It's got a vector in there, but the symbols, these absolute value bars, are telling you, take the components, square them, and take the square root. So this is a single number, 1 over a number, right? So obviously this doesn't work for vectors, 0 vector, because that vector has no direction, so having its direction and unit length doesn't really make any sense. But for all other vectors, this will give us a unit vector in the same direction, okay? Let's try this in 2 dimensions just to be able to draw it nice and easy. Let's say I have the vector v equals, let's make it 3, 5. So we might imagine this is a vector that goes 3 units to the right. Sorry, let me draw it a little better. 1, 2, 3, and then 5 units up. So maybe something like this. Well, let's find the magnitude of v. That's going to be the square root of 9 plus 25, which is the square root of 34. So what is this going to be? Just below 6, right? 6 squared is 36. So this is going to be a little bit below. I'm just going to estimate it top of the head. Let's just call it 5.9-ish. I just want to make a reasonable picture. 1 over the square root of v times the vector v is going to be 1 over the root of 34 times 3 times the vector 3, 5, which is going to be the vector 3 over root 34, 5 over root 34. All right, if we approximate this, this is about half a unit long, and this is going to be about a unit long, a little bit less, right? So something like, well, my picture is pretty off. Maybe something like about this. Okay. Let's check the length of this vector, right, to guarantee this. So I want to take the magnitude of the vector, 3 over root 34, 5 over the root 34. Take the magnitude of this. I square this. 3 over the root 34 is 9 over 34 plus 25 over 34. Gives me the square root of 34 over 34, which is, of course, 1. So this is indeed a unit vector, right? And since we've only scaled the vector v, it's in the same direction. Okay, that is it for this one. We'll do a lot more in future videos with some applications, and of course, we're going to complicate things further as we go. Okay, I will see you next time.